DACs, or DACs, convert digital words which are made of bits and bytes to analog voltages, which are of course continuous in voltage and time. I should be careful to point out that this is not something else that's often called also a DAC or a DAQ. That instead stands for a digital acquisition system, which confusingly is effectively often an ADC. So we talked previously about, when we were discussing analog to digital converters, going from a voltage in this digital or in this analog domain to digital words. And those digital words would have some M bits, which means effectively that they'd have 2 to the M different code possibilities. The analog side of things would of course have a full-scale range associated with it as well, which would be some maximum possible input voltage and minus a minimum voltage right here. So maybe my max voltage is up here and my min voltage is right here. And an ADC went this way, right? We were converting from an analog voltage output, this continuous in amplitude and time signal, and we were converting that to digital words on something like a microcontroller that would be on your Arduino, for example. Now, what we're going to be concerned with here is the opposite direction. So going from the Arduino back to the real world. And that's where the DAC is going to come in, or the digital to analog converter. And similar to the ADC, that's going to also have some delta T or some clock signal associated with it as well, because it can only do it at a certain speed or a certain rate. It can only change the output voltages at a certain rate. So I'd also be remiss not to mention that the Arduino Uno that you're most familiar with doesn't have a real DAC associated with it. So what you've used in the past with your analog rate commands have been kind of a fake digital analog to converter. So it's one way of doing a digital analog converter, but not a very good one. Other versions of the Arduino board, so there are a bunch of different varieties of Arduinos with different microcontrollers associated with them. Some of those actually do have a DAC, and one of the ones that we'll talk about here is the Arduino Due, D-U-E, and that has a 2-channel 12-bit DAC associated with it. And so we'll talk a little bit about DAC performance in the context of that other Arduino. Similar to the ADC case, we can think of this in terms of an ideal conversion. But in the case of a DAC, on our x-axis, we're going to have the binary input. Remember, there's a digital input to the DAC. And on the y-axis, we're going to have our output voltage that we'll have from the DAC. And this will be multiplied by VFSR, so I've provided a fraction of that full-scale voltage range on the y-axis. And in an ideal world, we'd have an infinite number of codes coming in, and we'd have a perfect mapping between the highest code and the full-scale range of our output voltage. Now, in reality, you might have something that looks a little bit more like these red dots here. So if I have a code of 0, 0, then I have an output of 0 volts. If I have a code of 0, 1, I have an output of 1/4 VFSR, output, a binary input of 1, 0, and this is for a 2-bit DAC, I should be clear. 1, 0, then I'd have an output of half of VFSR, and if I have an output of input of 1, 1, I'd have an output of 3/4 VFSR. And remember, this is not really drawn as a kind of continuous function because my inputs here are discrete. I have digital inputs, and so they only exist at certain points here. The output, of course, is continuous. So this yellow line, of course, is our ideal conversion, and these red dots are our reality. And this is based on a 2-bit DAC. We can obviously have more bits and have a better approximation of that ideal conversion. So in reality, these DACs are going to have a limited number of input codes based on the number of bits associated with the DAC. In this example, M was equal to 2. So also in this example, code 00 went to 0 volts. Let's say I have a VFSR, for grins, Let's make that equal to 5 volts. So 0, 0 converted to 0 volts. 0, 1 would convert to 1/4 of that, so 1.25 volts. 1, 0 would convert to 2.5 volts, and 1, 1 would convert to 3.75 volts. All right, so I never got up to the full scale range in this case. I only went up to 3.75 volts, and different DACs will set things up differently, as I mentioned. So I might have another DAC that would place the 0, 0 code at 1/8 of VFSR, for example, or even at 1/4 of VFSR. So this is going to be shifted depending on the DAC implementation in the particular DAC that you're using. In general, though, given some digital code, if I'm interested in figuring out what the resulting voltage output from the DAC is, so my V out is going to be some fraction based on the code of the total number of bits times that full scale range. Right? And once again, this might change a little bit depending on the implementation, but this is a good rule of thumb. So a quick example, if I have a full scale range of 5 volts, and I have a 10-bit DAC in this case, and let's say I'm outputting a code of 351, sounds like a good number. So my V out in that case is going to be 351 divided by 2 to the 10, or 1024, times 5 volts, or about 1.71 volts.